Hi everyone, this is Dr. Sudha Rani, working as Associate Professor in the Department of Electronics and Instrumentation Engineering in VIGNANA JYOTHI Institute of Engineering and Technology. Let's see capacitive transducers. The capacitive transducer, the principle is based upon the parallel plate capacitor. The parallel plate capacitor, we can see the picture here. It has a top plate and it is a bottom plate. Between these two plates, dielectric medium is sandwiched. Here L is equal to length of the plate and W is the width of the plate. The capacitance we can represent C is equal to epsilon A by D, where epsilon is permittivity of the medium. This epsilon we can write epsilon R into epsilon naught, where epsilon naught is relative permittivity and epsilon naught is permittivity of the free space, that is 8.85 into 10 to the power of minus 12 Faraday per meter, and D is equal to distance between the plates. That means here this is the D, the distance between the plates, this plate and this plate, and A is overlapping area of the plates. This plate, this is the plate and this is the plate, the overlapping area. So A is overlapping area of the plate and D is distance between the plates and C is the capacitance. Now this capacitance is going to vary with respect to these parameters. One is overlapping area of the plates, distance between the plates and dielectric constant. The capacitance, whatever it is measured, can be measured with the bridge circuits. Now, the impedance of the capacitance transducer is XC is equal to 1 by 2 pi FC, where C is equal to capacitance and F is equal to frequency excitation in Hertz. Let's see one by one here how the capacitance is changing with respect to change in the overlapping area of the plates. Now, how this capacitance is changing with respect to change in area of the plates. The capacitance here directly proportional to overlapping area of the plates. So C is proportional to A. This A is overlapping area. In this we are taking one example here. These are the cylinders. This is outer cylinder and this is inner cylinder. This outer cylinder, it has a diameter D2 and the inner cylinder, it is a movable cylinder. It has a diameter D1, where D2 is equal to the inner diameter of the outer cylinder and D1 is equal to the outer diameter of the inner cylinder. When the movable cylinder is moving towards this direction, then what happens here? The overlapping area of the two cylinders are more. When the overlapping area A is more, that means the capacitance is equal to maximum. When this movable cylinder is towards this direction, then what happens? The overlapping area is less. The capacitance is automatically, it is less. Now, if you see here, we can write the formula for the capacitance. C is equal to epsilon A by D. This is the general formula. Now, C is equal to, for the cylindrical, for these two cylinders 2 pi epsilon x by log E d2 by d1. In this condition, what is x is here the overlapping area, the length of the overlapping area. Now, if you see here, 2 is constant, pi is constant, and permittivity epsilon is constant, d2 is constant, and d1 is constant. So we can write C is equal to, let us take this one entire, this is a constant representing with K into X. That means capacitance is proportional to X. Now let's see what is sensitivity. Sensitivity is equal to change in output by change in input. What is change in output? Change in capacitance by change in input, that is X, dou C by dou X. Now this is equal to, the sensitivity is equal to constant. The sensitivity is equal to constant. Now let's see second example, parallel plate capacitor. In parallel plate capacitor, we have two plates are there. One is a fixed plate and another one is a movable plate. In fixed plate, it is the fixed plate and it is the movable plate, and where X is the overlapping area. And when this movable plate moves towards this direction, the capacitance increases. When the movable plate is moving towards this direction, it is decreases. Now for the parallel plate capacitor, as we know that C is equal to epsilon A by D. Now C is equal to epsilon, what is A here? Overlapping area, where A is equal to overlapping area, that is we can write X into W. What is X here? X is equal to overlapping area of the plates and W is equal to width of the overlapping plates. Now sensitivity is equal to S is equal to dou C by dou X. Now if you take our formula, sensitivity is equal to epsilon X W by D. Now if you do the sensitivity here, if you take the sensitivity, dou C by dou X, that is equal to epsilon W by D, that is farad per meter. Now the sensitivity is equal to constant, and if you take the fractional change in the sensitivity, okay, that is dou C by dou X into the capacitance. So what is dou C by dou X? That is equal to epsilon W by D. Okay, so let's write S bar is equal to epsilon W by D. And what is C here? C is equal to epsilon, I can write here epsilon W by D into 1 by epsilon X W by D. Right? Now so we can cancel epsilon W, and this D will go here, and this one cancel, and we will get the fractional sensitivity is equal to 1 by X. Now this fractional change, or this fractional sensitivity is equal to 1 by X. This type of arrangement can be used to measure the linear displacements. It is from 1 mm to 10 mm. Next example is angular displacement. In angular displacement, here we can see the arrangement. One plate is a fixed plate and another plate is a mobile plate. When this mobile plate is moving towards this direction, means it is occupying the more place. The overlapping area is equal to maximum. When it is overlapping area is equal to maximum, the capacitance is equal to maximum. Now, when the overlapping area is equal to minimum, the capacitance is equal to minimum. Okay, now it is called as a theta, that is angular displacement. How much it is covered or how much it is overlapped here, that is linearly proportional. Now, if you see the relation between the angular displacement theta and the capacitance, here it is a linear relationship because C is proportional to overlapping area. Now, the value of maximum capacitance can be represented. C max is equal to, the general formula is epsilon A by D, where epsilon is permittivity and the area of the plates is pi r square, and here it is D. Why it is 2D? Actually it is a 1D right here, but it is a 2D because here we are not using the fixed plates. We are using the plates, it has a arc shape. Now these two plates, it will act as a series. That's why we are getting 2D here. Now let's see this theta. The theta, that is the angular displacement. This is the angle theta, right? That is C is equal to, now it is epsilon, as it is we can write permittivity and it is this r square, this radius, and this is the angle. We can represent with theta by 2D. Okay, this is about the angular displacement. And then let's see another example, that is how this capacitance is changing with distance between the plates. In this one, we are considering two plates. One plate is a fixed plate and another plate is a moving plate. The distance between the plates is small t. As we know, C is equal to epsilon A by D. When distance between the plates is increasing, then it is when it is increasing, that means when this moving plate is moving towards this direction, that means D is increasing. When it is increasing, the capacitance is decreasing. When the distance, here they say the distance displacement is moving, means when we are moving this plate in this direction, here what happens? This distance is decreasing, right? So C is increasing, capacitance is increasing. That means C is inversely proportional to distance between the plates. So if you see the relationship here, X versus this one, X is here displacement and it is capacitance. It is inverse relationship. It is inverse relationship. Now let's see one more example, how this capacitance C is varying with distance between the plates. So in this condition, here we are taking capacitive transducer using a cantilever spring plate. So here we are taking cantilever spring plate, this one, and in between dielectric medium is used. When one plate is moving towards this direction, that means in this direction, like this, in this direction. Now the distance is more. Then in this case, the capacitance is, when the distance is more, that is C proportional to, inversely proportional to 1 by D, right? So when it is increasing means it is decreasing. The capacitance is decreasing. And one more example is the capacitive transducer using quartz diaphragms. In this example, 2 quartz crystals have been taken here, and this will act as a diaphragms, and the dielectric, if the dielectric medium is air. Okay, so when there is a displacement is applied on these silver quartz diaphragms, so what happens? The same principle, C is inversely proportional to D. When it is increasing means the capacitance is decreasing. And suppose if we create vacuum here as a dielectric medium, now it will exactly act as a absolute pressure. You can use to measure the absolute pressure. And the temperature coefficient of the quartz material is very high. That means when there is a change in the temperature, there is a change in the capacitance. It is very sensitive to the temperature, and it is very useful to measure the capacitance. And one more example is this capacitive transducer used to measure the rotational displacement. In this one here, we are using a rotor and a stator. When the rotor is rotating in counterclockwise direction, what happens here? When this rotor is rotating in counterclockwise direction, it is giving the angular displacement. When this rotor rotating in the counterclockwise direction, the capacitance is increasing. So like this we can measure the angular displacement. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.